Yeah, thanks, AJ. Yeah, I'm Matt Mattina. I run ARM's ML Research Lab. We're based actually here in Waltham, and we started this group end of 2016, beginning of 2017, with a remit to first and foremost, feed ARM's product roadmap, especially with an eye towards ML and AI, and also to kind of help build out the ecosystem, the research ecosystem around ML, and in particular, efficient ML inference on edge devices. So marketing makes me put this slide in always, and with a show of hands, how many of you know about ARM? Okay, good. So I don't need to linger on this slide much, but so ARM is a hardware IP company, right? So we don't build chips, we design hardware blocks that we then license to silicon partners, semiconductor companies that put these blocks down on a SoC, and then they either put that SoC into the end device like a phone, or they'll sell that on the merchant semiconductor market. And so what do I mean by hardware? So these are like our cores. That's sort of the main hardware IP block that ARM licenses. So these are the Cortex-A class cores. These are sort of beefy cores. Some of them are out of order cores. They run, Linux, and inside of your phone you have several of them. So 95% of the world's mobile phones have ARM at their on the processor. I don't know what the other 5% are using. But yeah, so in addition to those big cores, we also sell microcontrollers, and I'll talk a little bit about those during this talk. But these are much smaller, much lower power, much less area cores that go into deeply embedded devices. We also license GPUs. So Mali is actually the number one shipping GPU in the world by volume. So these, again, mostly into mobile devices. And so, it's actually kind of staggering to think about it, but we've shipped, there's been 146 billion ARM-based chips shipped to date. That's a lot. So we ship a lot of processors, and really what that means to me is most of the world's ML, inference anyways, is actually running on an ARM core at this point in time. And in 2018 alone, there's been shipped 23 billion ARM-based chips. So that's ARM, big picture. So the lab itself, our remit is to be a technology leader, especially on efficient inference. So we're really, job number one for us is efficient inference on mobile, deeply embedded devices. We're also looking at things like distributed machine learning, so things like federated learning, but I won't touch on that work much in this talk. So we have three main threads of research, like efficient hardware for ML. So this is like, how should accelerators be built, right? What does the microarchitecture look like? And I'll speak to that in a few slides. Also, of course, instruction set architecture and data types. So things like bfloat 16, the new 16-bit floating point format that's spends more bits on range than precision. That's definitely in our remit, and just more run-of-the-mill ISA additions like matrix multiply and vector ops that we can put into our cores to make ML run faster. In particular, ML really, the action is around neural nets for the most part, and that's what we're focused on. On the efficient hardware thread, We also are looking at emerging device technology, so things like compute in memory and analog implementations that could offer better performance per unit area, per unit watt versus straight up digital CMOS. That's in our purview as well. Then shifting away from the hardware side, we spend more and more effort actually these days is on the model, what we're starting to call model conditioning, model design optimization. Like, I've got a model, or I want a model, I need it to run on a constrained platform. This is not going to run on 32 NVIDIA GPUs in the data center. It's going to run on my mobile or on my light bulb. What do those models look like? How can we make them fit in the cost area, power envelope? So more and more we're spending effort on that side of things. This is beyond, pruning and quantization, but even further afield. And as I said, edge to cloud and ML systems. So this is further out research around less about inference on the device and more about training on the device. What are the use cases for actually doing either incremental learning on your device, so it is better at recognizing the nuances of your interaction with the device, and also aggregating models together from many little devices that may have learned something about their environment, aggregating those together, possibly in the cloud, distilling those models and pushing them back out to the end devices. So these are our research threads, if you will. I'll go back a slide. Or not. Well, I'm gonna focus on two pieces today: the sort of the hardware side and the AutoML model optimization side. So I think AJ set this up really well in his talk. So I don't think I need to spend too much time on this, but it's important just to be clear that there's this contrast between what you do in the cloud, where you have lots of resources. The speaker from Facebook even mentioned, yeah, they burn a lot of power, but it's just not the number one concern for them. So you got a lot of power. Hopefully your data center is built next to a nuclear power plant or something like that. You've got a small number of processor targets, generally, at least for training. And that's very different than the edge, where you've got sort of a much more heterogeneous hardware, and most importantly to me, you're in a very different environment. You're very constrained by power and thermals, and so at a high level, what we're focused on is, okay, you've trained this. You're a data scientist. You've trained this model in the cloud. Now you want to sort of deploy it on the edge in inference mode, and what are the things that you need to pay attention to? So that segues into sort of the meat of this, which is what really are the hardware challenges with neural net inference on the edge. And again, I think AJ and Facebook Nick did a nice job motivating this as well. So. And also the GE talk. So these models on the compute side, they demand billions of max, so multiply accumulates per inference, right? So if you just look at like Inception v3, which sort of was a state-of-the-art network 6 months ago, it takes like 3 billion max to push one image through it. And as that's not the full story, though. It's like, as G mentioned this morning, well, if you want to do 2,000 frames per second, that's like what, over 3 teraops of multiplies to keep up with that frame rate. So it's the max per inference, and it's the frame rate that you want to run at. So most of these operations, by the way, are in the convolution layers. The fully connected layer at the end tends to be more memory bandwidth bound, but most of the work is in the convolution layers. Most of the work is multiply accumulate, and you need with the high frame rate, you need over a teraop per second for many applications, and that's a lot of multiplies, right? If you think about like an ARM core, an x86 core running at a couple of gigahertz, maybe with a vector unit, they can do 8 or so FP ops. So that's, 16 GOPS for a core. You're not going to get to a tera op with that. That's the compute side. On the storage side, the models are big. This graphic kind of tries to show that here. So what the bubble size is the sort of the size of some models. Now VGG is particularly enormous, but something like AlexNet, the original network that started it all, that's down here. Google's mobile net stuff is getting better in terms of size, but isn't as accurate as some of the larger models. So in addition to compute, there's the storage component, just like fitting the model. And this becomes, again, particularly interesting for the deeply embedded stuff that I'll talk about a little later. And then the thermals. So in mobile, we've got battery constraints and tight thermals. And one way I like to look at this, rather than just say it's the thermals, like if you look at, so I motivated like we need a teraop per second at least for some of these networks. Okay, well, how do I get to that? Well, that kind of implies to first order, I need to read a trillion values out of an SRAM per second to feed that. How else am I going to get that kind of throughput? Well, if you're going to read at that rate from a sort of a normal SRAM in 16 nanometer, right there you've eaten up a watt and you haven't done a single multiply. So just feeding all the multipliers from RAM in kind of a naive way is going to consume a ton of power. So these are the high level sort of compute, storage, and power problems with getting efficient inference at the edge. So what has the industry done, or what has the research community done about this? And there's sort of these 5 main buckets that are now actually becoming pretty standard in state-of-the-art accelerators for edge devices. This was alluded to earlier, reduced precision, so we can take this model that was probably trained on an NVIDIA GPU with FP32 weights and activations, and it's been motivated and shown in the literature now that you can reduce that to like an 8-bit for deployment at the edge with a pretty minimal loss in accuracy for many networks. Some RNNs, this doesn't work so well, but generally you can quantize your model down into 8. We're looking at going even lower, like to 4-bit values. And you can do this generally with, let's say less than 2% or less than 1% loss in accuracy. Now I say 4x throughput improvement. That's not really true. I mean, that's based on the argument of like, well, I had 32 bits. Now I have 4 8-bit values in that same area. But for parts of the network that aren't, MAC bound, you don't get that speed up, but your upper bound is at a 4x throughput. On the data reuse side, this is actually the key, and it kind of harkens back to that 1 terabyte per second on my previous slide, burning a watt of power. The key in the microarchitecture is to exploit the reuse of convolution weights, right? Convolution is taking a filter, smallish, maybe a 3x3 filter by 16 deep, and sliding it over the input feature maps. So you're reusing these values over and over and over again, and it's sort of madness to keep reading those from a register file. So that one point really drives the microarchitecture of state-of-the-art accelerators, whether it's systolic, where I'm going to read from an SRAM the filter values and then move it across this spatial array, or other sort of designs where I locally cache the filter values and then use them over and over again as I slide activations past. But that one piece actually is like the first thing the architect thinks about when building one of these accelerators. Weight compression, this was alluded to earlier. this is important for, again, to that terabyte per second point, compressing the ways that I don't mean quantizing, but rather there's lots of zeros naturally arising in these networks from ReLU, the rectified linear unit activation function that clips at zero, clips the negative values. So weight compression will save me in bandwidth and power. So some of the other more esoteric optimizations involve transforms. So, matrix multiply is a sort of naturally n-cubed operation where you're multiplying two matrices together to get an output matrix. Many accelerators now from ARM and others support Winograd transforms. So this transforms the matrix multiply into this Winograd domain. It's kind of like an FFT, and you reduce the number of multiplies you need to do, and you can make that an order n squared operation. And finally, sparse computation. So there's lots of sparsity in these networks. It arises from both ReLU, as I mentioned, and from pruning, as I think AJ and Nick mentioned. You can prune these networks sometimes to remarkable degrees of sparsity, like where you eliminate 90% of the weights, and the network essentially gets the same accuracy. That's an opportunity, right, to skip over those zeros in the computation. Like, don't multiply things by zero because we already know the answer. So this is standard. Those are sort of becoming standard in the industry. What we looked at recently in research was going even further. So we had this idea of taking transfer learning and exploiting it in hardware. And what I mean by that is we want to train a network like, say, MobileNet on ImageNet. And then we want to lock down the early layers in the network and allow retraining only on the later layers in the network on the target task. So with the observation being, well, ImageNet, if you learn ImageNet, maybe you've learned some fundamental things about vision, and that will carry over, will transfer to other data sets that aren't ImageNet. And can we exploit this in hardware? So we said, what if we train MobileNet on ImageNet, lock down those early layers into hardware, actually. So build gates out of those early layers because we know the weight values now. We've trained it on ImageNet, and allow the back end piece of this to still be programmable. So you've got like this fixed portion. You've got this fixed portion where we've trained this trained MobileNets on ImageNet, locked those down into a data path, and then the later layers will be trained, based on the particular task. And those will be executed on a programmable CNN accelerator. And why do we want to do this? Well, we want to do it because the hypothesis is we can achieve higher throughput, lower power compared to a fully programmable accelerator, because the stuff I'm crunching into gates is going to be much smaller than a general multiplier. For example, like if I know one of the operand inputs is 7, well, I can exploit that in the hardware. So that's the hypothesis, and we called this Project Fixie. We published this work this year at SysML, and remarkably it worked. And the way we did the comparison is we kept it ISO area, right? So imagine you have a 3 millimeters squared of area, fully programmable, like NVIDIA DLA accelerator, versus a same amount of area, but now some of it's fixed, and I've shrunk the programmable part. And so there's two things to point out here. So specifically on using MobileNet as the MobileNet trained on ImageNet, we can get about 50% higher tops per watt by fixing those first 4 front-end layers. So in other words, this guy is implementing those first first 4 layers, and the back end is executing the remaining, I think it is 8 layers. And we get 50% higher performance with essentially no accuracy loss on the new data sets, which are SciFar 100, the street signs, the aircraft data set. So they're still vision-y data sets. It's not like this is speech or something. So you'd expect it to do pretty well, and it does. And by the way, as we fix more and more layers, we get more benefit from a TOPS per watt standpoint, but you start to pay for it in terms of accuracy. So this was kind of cool. Oh, by the way, we wrote this tool to take a TensorFlow protobuf, essentially the description of your model, like here. You can specify, these layers I want to put into Verilog, and then we open source this tool called Deep Freeze, which takes those layers and actually spits out Verilog that you can then synthesize into a netlist. And that's you can find that code there. Okay. That's the hardware, some of the hardware, forward-leaning hardware research that we're doing in my group. Switching away from hardware now to sort of more the model conditioning and optimization side of things. I don't know if anybody, whoops. Yeah, we'll see how good you are. This is actually the AlexNet, the network that started it all back in 2011, 2012. And the thing I, think every time I see this is like, well, here's the layer specifications and this number of filters and this, that, and the other thing. It's like, how did, Alex or Jan LeCun come up with that? Like, why were there this many output feature maps at this layer? Why not half that? Where did that come from? And it came from their intuition and stuff. And that strikes us as a really hard problem to scale. Like, there's not that many Jan LeCuns, so how are we going to sort of automate this? And in particular, how can a non-expert design such a network? How do they know it's the best network? What about other constraints? Like, what am I going to execute this network on? Like, is this going to fit on my Cortex-M deeply embedded device? So the high-level question is, we want to automate this, the network architecture search, as this is called, or AutoML. We want to automate it, and we want to inject hardware knowledge into that loop. And AJ mentioned this in his talk as well. So Google's looking at this, and we collaborate with Pete Warden and others on this. But yeah, this is what we want to do. Like, I have a data set, or a customer has a data set. They want to generate a state-of-the-art CNN for it, but they also want it to fit on like a Cortex M7 deeply embedded SoC. That's a hard problem, and we were researching that. And this is our first publication or public disclosure of this. We developed a framework called SPARSE, which stands for Sparse Architecture Search. The British guys on my team think this is funny because it says arse in the name. Yeah, so we're targeting microcontrollers for some pragmatic reasons. Like, it's much easier to work with those because we can constrain the space a bit. But for those of you who don't know, a microcontroller, like, here's an NVIDIA 1080 Ti, right? It's got 11 gigabytes of memory, 250 watts of power, 10 teraflops per second. Well, down here, these are microcontrollers, right, where you've got 4 million megaops per second and 2 kilobytes of memory. So these are just dramatically different platforms. And we wanted to see if we can automate the search for CNNs that fit on microcontrollers and deliver state-of-the-art accuracy. And this project is dynamic. It's running now, but our early results are pretty encouraging. So we've developed this framework that we will be open sourcing, and we'll be presenting it in detail at NeurIPS this year in Vancouver. Essentially, we use a Bayesian optimizer to generate candidate networks that meet the tight constraints that we give it. In particular, we give it working memory constraints. So we say, you've only got 4 kilobytes of working memory or 2 kilobytes of working memory. Therefore, your output feature maps, from a layer can never exceed 4 kilobytes at any given layer, right? It always needs to fit. And we're generating some pretty encouraging results for that. So, for example, on the Cars 4K, this is a handwriting data set like MNIST. What I'm showing here on the x-axis is the number of parameters, accuracy on the y-axis, and these other blocks here that you'll notice have lots of parameters are things like k-nearest neighbors, bonsai tree, gradient boosted decision tree. These previous methods for solving this data set at high accuracy require lots and lots of parameters. We generate a Pareto or Pareto curve of different candidate models along the way. So this is our solution. So for example, at a 60% accuracy, we can generate a model that has, an order of magnitude fewer parameters than a bonsai tree. So we're going to we've posted this on archive, and it's been accepted to NeurIPS, and we're going to talk about it in detail there. So just to give you some idea of what we've been publishing lately, this is some recent publications from our lab. This is the work on sparse architecture search. As I mentioned earlier, we're looking at very low precision, again, with a view towards how do I reduce parameters even further. So we're looking at quantizing networks down to like 4-bit weights, 4-bit activations. Can we do that without tanking accuracy? We have some encouraging results on that. Yeah. This is our research lab here in Boston. It's really a great group of people. It's kind of a mix of proper ML PhD types who can, generate lots of mathematics for our papers, and a bunch of sort of seasoned hardware people from places like AMD, Intel, and NVIDIA. So it's a good combination of hardware folks and ML theory people. And I'm happy to take questions.
Thanks, Matt. You had a question? Okay. Well, one question was, is this related to, or is your work also going into the ML IP that ARM has floated out now, which can be used by customers who are building SoCs based on ARM IP?
Yeah, it's a good question. So that's sort of our, first and foremost, that's the objective of this research group. That's the mission, is to deliver into their roadmap, right? So they've released the first version of an NPU, which gets 4 teraops per second. Then what, right? So our job is to sort of feed that technology cache. So what could they do next? Could they use posits, for example, to accelerate computation? What new sparsity techniques do we have coming? So yeah, our main remit is to sort of build technology, proof of concepts that they can then productize into future NPUs from ARM.
Got it. Thanks.
So I have a question about deep freeze. So it looked like you could take in a model and then spit out Verilogs to design a chip specifically for that model, and you can essentially create bespoke chips for your architectures. Do you know of anyone who's actually doing that? Because that seems really interesting.
I know of startup companies that are doing that. I know that DARPA is interested in that. Do I know specifically of anything on the market today? No, I don't know of it, but I bet it's there, because if you're just going to do one thing with your, I mean, there's a downside to this, right? Which is, well, you just burnt something into silicon. That's all it's ever going to do. But there are markets where that's okay, right? I'm always going to be a smart light bulb, and what I really care about is the utmost in power efficiency. So I think for those types of applications, it makes sense. But I can't give you like, oh, company blah does this.
Thanks.
So I have a question on this. It's a trade-off, right? Accuracy versus how big the model is, and deep freeze and so on. But one thing I've consistently struggled is how much of the real product people have actually shown a willingness to give up some accuracy. Because I've always seen that when it really comes to launching a product, nobody wants to give up any accuracy because they've worked really hard to get that 1%.
Yeah. I mean, I think this is less of a hardware question and more of a model question, because like most of the discussions around this, like sacrificing accuracy, come from the model conditioning space, like quantization, right? Which, everybody is talking about. Well, when you quantize from FP32 to int8, in most cases, you are going to sacrifice some accuracy. And yeah, I think your point is a good one. There may be like an allergic reaction to that, right? I guess, again, I would say it depends on your use case. Like if you're a vision thing that's checking for bad potato chips, do you care if your next bag, has a 0.5% probability higher of a bad potato chip? Maybe not. That might be worth the trade-off. So I agree with you. There's an allergic reaction to that. I know Google is trying to formalize this a little bit, like saying how much accuracy loss is okay. I think it's a good question. I think it's going to require like some almost like standards body to kind of say like, these losses are acceptable, these losses are not. But I think at the end of the day, it's going to come down to the use case. Like, I can imagine a military use case where no, I can't lose any accuracy, but potato chips maybe I can.
My question is about you mentioned the weight compression, and
Yep.
even deep freeze and weight compression can reduce the coefficient bandwidth. But what about data? Don't you compress the compressed data as well?
Don't you compress the compressed data?
Yes.
Well, you're talking about like the input frames coming in. Yeah, I mean that could be compressed. We assume just like or RGB data coming in for these cases, these image cases.
About the hidden layers and other.
So like in the network.
Exactly.
Yeah, so it's a good idea to kind of try to compress in the intermediate layers of the network. We didn't do that in this work. The big opportunity for that is, compressing or quantizing the activations further. Our research into that has shown so weights, we feel pretty good about, dropping below 8-bit quantization. For activations, when we drop below 8-bit, we see a pretty significant accuracy fall off, and it's very sharp. So like when we try to compress in the intermediate layers, the activations down, accuracy tanks pretty quickly.
My question is sort of an extension of one of the earlier questions. So with both the transfer learning exercise as well as some of the other sparsity in the hardware exercise, there's increasing literature on the fragility of many of these networks for either changes in texture, changes in position in such a way that actually for a lot of use cases could be pretty catastrophic. And once you bake into the hardware, it's going to be, there's no patching, right? So have you considered, or are you thinking about some form of diagnostic for discarded residuals or residual feedback into intermediate layers that might help mitigate some of those risks where they really could end up mattering on either algorithmic bias or data bias in places where that could be
Yeah.
a pretty big deal, right?
Yeah, this is a very good question. I would say, my short answer is this is an open research question. I think, I've looked at some of the adversarial examples, and those in particular are very scary. Like these are 1 pixel flips in an image, and the model goes from, classifying it as a giraffe to an airplane, and no one knows why, right? That's the even scarier part. So, well, why did it do that? Well, I don't know. To your point about the fixed function stuff, I feel like we have a get out of jail card there, which is don't fix the whole network, right? Fix some early layers that might be doing edge detection and that sort of thing, so that if you have examples that you're getting wrong, right, well, you've got these back-end layers that you can retrain and download a new model that fixes that particular example. So that's what on the hardware side, personally, like if I was building a chip, I would be very careful about burning the entire network into gates, and I have no way to change the weights thereafter. That just seems like you're setting yourself up for a problem. Yeah, allowing some patching, fine-tuning of parameters, some get out of jail card where, to your point, like if you get some of these examples that you're just classifying wrong, you can fix it.
Thanks, Matt.
Okay.
Sorry, we can probably take other questions
Yeah, I'm happy to
offline because
find me during the break. Yeah.
Yep.
Okay.
Thank you.
Thank you.
So our next speaker is Jonathan